highest average, Friday the worst, in general, because you get the weekend to study. That's just my experience. Usually on Friday, you have a lot of stuff due, but I don't know. Some people don't like a Monday test because they work over the weekends or something, but I'm just telling you, from my personal experience, that's what I believe I've observed.
Well, it must be postponed to like July.
Sure.
We can't do a Monday test.
Huh?
It's just we have off not next Monday, but the Monday after and the Monday after that.
Okay. Well, that's sort of like the same thing, isn't it?
Yeah.
So a Wednesday test
Yeah.
after an entire Monday off is the same thing.
Yeah.
But
A lot of times.
give me a date you'd like anytime. Our last day is towards the end of July, isn't it?
Hmm?
Last day of class before final exams is somewhere around the end of July, isn't it?
Yeah.
I don't remember the date. Go ahead. You got one for me?
I'd be fine with the 21st or the 28th.
Monday. That's a Monday.
Those are both Wednesdays.
Those are
Oh, Wednesdays? All right.
Because
so
we have those Mondays
this
off.
is June, right? Or June, right?
Yes.
June 21st, did you say?
Yeah. Or I'd also be fine with the 28th.
Yeah, that would
21st.
that would be.
I would
Yeah.
go, but I'll put them all up there if you want. The 28th, give you a little more time. That's a Wednesday too, right?
Yeah.
All right, so what is the date? What is it, Juneteenth or something?
Yeah. On the week of the 21st, that's our only class day. On the week of the 21st.
So the 28th might be ideal. You got over a week to
Yeah.
basically dead time, right?
Yeah.
Yeah.
All right, why don't we just do a show of hands? How many want it on the 28th? You look with me, make sure. Huh? We're voting. If you want the test on the 28th, raise your hand. I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9. This is unanimous. It's a no-brainer. All right, that's test
I think
day.
we'll be all the way through chapter 3 by that
I don't know
time.
where we're going to be. Here's what happens. When we go to the test, the lecture before the exam, that material is not covered, but 2 lectures before, like the lecture before the exam, what I do is do a review. All right, so
Okay.
you got me on that?
That makes
So-
sense. No, that's fine.
All right, so, y'all, can you do me a favor? How about send me an email, Dr. Baginski, we have voted on the test. It is on the 28th of June. And then I'll make sure if somebody's not here, I'll forward it to them. I think we're missing 1, maybe 2 people.
So that means we have today, Friday, and then all next week to do new material. And then the week after that, that is our only class day, so that's our review day. And then we'll have the test the next class day.
21st, then the 28th, bang. You guys got it good. I like that. Got enough time to study for really an accounting test. I mean, sorry, what do they call that thing? An actuarial test. You know that. So all right, so now, I'm glad we settled that. That was painless. I'm sorry I was a minute late. I will do my best to be on time now. All right, so questions about homework. We did the transit. We started into EMAG. We started into electrostatics, right? Any questions? All right, lectures. Did you have one? Anybody? Did y'all try those things?
Yeah, but you didn't list the answers.
For 3?
Yeah.
Send me an email about that then.
Okay, I'll just have it in the same email.
Dr. Baginski, you are so lame. Forgot to post the answers. Anyway, go ahead. Did you have any questions? I mean, because we can do, why don't we do it? Which one would you like to do in chapter 2 or 3? Into chapter 2, but you got those answers. Or 3. Chapter 2, we did pretty much the bounce business, huh? Right?
Yeah.
Yeah, bouncers.
Did you have something you wanted to
No.
see? All right, chapter 3. How about chapter 3? This is again electrostatics. Now we're getting into the real meat of this course, electrostatics and magnetostatics. The bounce stuff you could have done in circuits if you had time. Nothing?
If you want to work a problem, you can work 3.4.
All right, give it to us.
Okay, so Q1 is 0, -3, 0.
This is the position, 0, -3, 0.
4 nano, and it's 4 nanocoulombs.
It's 4 nanocoulombs.
Yes.
Small. Q2,
Q2 is the same except it's -3, except it's +3.
0, 3, 0, 4 nanocoulombs?
Yep.
Okay.
And then Q3 is 400 at 1 nanocoulomb.
All right. Now remember, we want, what does he want? The force on what?
Oh, yeah, you're right. Force acting on Q3, then the same after changing Q2 to -4.
All right, here's what we're gonna do. I'm gonna set this up, but instead of getting the force, I'm gonna get the electric field on Q3. Here's why. Once I have the electric field, I just multiply by that and I have the force.
And he also wants the electric field, yeah.
Well, we're gonna go get the electric field first, all right? So I'm gonna ignore this one right now. Now, I'm gonna show you where these are. So if we do 3D here, try to draw this. By the way, if you have engineering paper, it really helps sometimes to see this. I'm gonna call this X, this Y, and this Z. It's the right-hand coordinate system. So Q1 is at 0, -3, 0. The way these things are really numbered, it's Q is X, that's the X, Y position, and Z position of the charge, the way I'm showing it. Y'all follow me? Okay, so Q1 is at 0, -3, 0. All right, 0x -3y, and 0. So this is Q1, and that's 4 nanocoulombs. I'm just trying to show you this. This is Q1. Q2 is at 0, 3, 0, and it's 4 nanocoulombs. So come over here. And this is 4 nanocoulombs also. And they want the electric field at X equals 4, 0, 0. So what they want is this. I want the electric field. They want the force. We'll get that too. So 3, 4, right? Yeah. So this is at 4. And this is where we want the electric field. And then we'll get the force. Y'all with me? Mm-hmm. Now just make sure you can visualize this. And I know at times I move too fast through this. Make sure everybody's got a good visual of what I'm asking. Got it, class? This is basic electrostatics. Most of you have had all this. What I'm going to do to give it a better viewing, I'm going to take this and flip it. Since everything going on here is in the XY plane, right? If I call this Y and I call this X, when I look at this at -3 and +3, I have 4 nanocoulombs. I have 4 nanocoulombs here. Here I have 4 nanocoulombs. Y'all with me? Now I want the electric field up a distance of 4. So I'm after the electric field here. I'm just trying to make sure you get a visual of this. You can imagine it. And I tend to be very, I encourage engineers to do is try to get a mental picture of what you're talking about. Especially with like random, I'm teaching that, and I'm teaching this. If you get a good mental picture of what's going on, you can sculpt the problem statement and get it right. Now, what I'm going to say is, this is a linear system, so the electric field caused by this at this point, plus the electric field caused by that charge can be added vectorially. All right, you can add them. It's just like you haven't had linear systems, right? This is a linear systems kind of problem. Now, I'm going to show you graphically what I'm talking about. If we just looked at this one right here, and since that's charge 1, call this, the electric field from this one, I'm just going to show you this, call this E1, all right? Now the electric field from this, since they're both the same they're same sense charges, the electric field from this would be E2. And you'll notice that this right here, since this is 3, that's 4, this is 5, and this is 5 is the radius distance, the distance from the charge to the point of observation. Y'all agree with that? You can square this, you get 16 plus 9, square root is 5. Y'all with me? Everybody? Now, can you all notice if I take that the horizontal components are going to cancel and the vertical will add? Can you all see this? Just do typical. So what I'm going to do is this. I'm going to calculate the magnitude of one of these two, say that one. Then I'm going to take the projection of that on the x-axis, and then I'm going to multiply it by 2. Does that make sense? Now we could get the vector E field here and the vector E field here and add them, but we get the same result. Do y'all agree with me? All right, so what I'm going to do here is first get the magnitude of E1, just magnitude, and that's really going to be K. K, of course, is 1 over 4 pi epsilon naught, and it's about 9 times 10 to the 9th. I'm just going to put that down. So the magnitude of E1 would be K. Actually, why don't we get E1? We'll just get E1. So E1 vector, right here, that's the electric field from this charge at that point of observation. First, it's equal to the K, right? Then it's the charge, Q1. Then I have to divide by R squared. I'm going to just put it down as R squared. And then I have to multiply by AR. Now, I'm going to expand this just a bit. Y'all follow me? Unit vector, magnitude squared. So I know that I'm going to put this as KQ1. I know AR is really R vector over R magnitude, so this becomes simply, I'll call it R cubed, and this is vector R here. Now what is vector R? You're going to see this. I like to going to just show you. Can everybody follow me what I'm doing and why I'm doing it? So what's vector R? Well, you take the coordinates of the point of observation minus the coordinates of the charge, of the location of the charge causing that, the electric field, and you subtract them. So in the x coordinates, it's going to be, what is it, 4, right? Minus 0ax, it's just 4ax, plus the y coordinate difference is going to be 0 minus a minus 3, or 3ax, right? Or y, I mean ay. And then as far as z goes, it's 0. Does everybody agree with that? Just make sure you see this. I tend to move quickly through this, but I'm trying not to. If you don't. How many see this right? Do you not see it, sir?
That's a little bit tough.
Here's what I have to do. I have to take the positions, the x, y, and z of this, minus the x, y, and z of this. All right, so what's the x coordinate of the point of observation? It's 4, isn't it? X is up. The x coordinate of the charge is 0, right? So it's 4, and it's in the ax direction. This is going to be, well, the y coordinate of the position of observation is 0, isn't it?
Yeah.
Minus, the y coordinate there is minus 3, so it's plus 3. And if you look at this, it's pointing in this direction. It has to be a plus x sense plus y sense. So that's it. So then I come down here and I get E1 equal to, and here we have K 9 times, somebody can give me this, 9. Over Q1, which is 4 nanocoulombs. I'm glad he made that choice. And then it's over R cubed, which is 5 cubed, right? So it's 125. And then you have over here, you have 4AX plus 3AY. And that's the electric field from the first one. If you wanted an actual value, right? Let's go ahead and get this. First, do me this favor. If I look at this, E1 itself, all right, this is going to be 9 times 4, because the 10 to the minus 9, 10 to the 9 cancel. So, let's see. That's 36, right? 36. And then it's going to be, just watch this. So that's 4 over 5 AX plus, actually, hold on. My bad. Yeah, I can get that. You check me on this. That's 4 over 5AX plus 3 over 5AY. Or it should come down to, what is it, 36 times 20. So 36 is going to be the scalar out in front. And, oh, my bad. This should be over 25. 36 over 25 here, and then it's going to be 0.4ax plus 0.8, my bad, 0.8 ax plus 0.6 ay, and I hope you understand my reasoning. Y'all with me? I'm just trying to simplify this now. This is going to be 36. 5 cubed is 5 squared times 5. 5 squared is 25, right? And then I leave a 5 here so I get something as fractions of 10, right? So I got 36 over 25 times that. That's the electric field, right? But we know that the what? The y components cancel, and the x. Go ahead.
No, I don't have anything. Sorry.
You look like
I was just spacing out. Sorry.
If you look at this, you all agree the y components cancel, but the x components add on or double. One of them is double. So I can say the electric field for the first part that he asked for part A is going to be equal to, it's just going to be in the AX direction. I'll put that down here. And then you're gonna have, for the x direction, it's gonna be 30 over 25 times 1.6. So it's gonna be, you can tell me what that is. Hmm?
It's 36.
It's 36, yeah, that's what I was gonna say.
It's 36. 36 over 25.
36
No,
and 8x.
no, it's 36 over 25, you wrote 30.
Oh, I'm sorry. Oh, 36 over 25 times 1.6x.
Yeah.
So what is that?
2.304.
And that's volts per meter A X.
Oh, wait, that is the
Huh?
wrong number.
So,
That's
Where'd
the
you
wrong.
get the 1.6 from?
2 times 0.8.
Oh, okay.
That's-
Gotcha.
I'm trying to go through that. I'm going to have to stop. Did you get that?
That's the number I got for the force.
No, that's the electric field.
Yeah, that's the problem.
That's the electric field. For force, you've got to multiply by Q.
Yeah.
Y'all with me? Oh, wait a second. We got, yeah, these charges, it is, this electric field is from this charge, and it is 4 nanocoulombs, right? Force, you'd have to multiply it by the charge at this point, which is,
Yeah.
what is it? Q2 is, or Q3 is 1 nanocoulomb.
Oh, yeah, no, so it's I got the same number, but times 10 to the negative 9. Yeah, yeah.
This right here is the electric field.
Yeah.
All right, so the electric field at that point for this one is going to be this. Now, what's the force going to be? That's E. All right, it's in the x direction. The force is just what? It's that electric field times the charge at that point. That's all it is. That's why I get the electric field first. Y'all with me? So what's the electric field times that, or times the charge? So I have a charge of 1 nanocoulomb. That means it's what? 2.304 times 10 to the minus 9, and this would be newtons per meter AX. Do you agree with that?
It's not just newtons. This is a force.
This, newtons, pardon. Gosh. Sorry, you're absolutely right. Newtons. My bad. You're right. Everybody with me? That's a force. By the way, that's a very small force.
Yeah.
I don't think of newtons. I think of pounds. And even though kilograms isn't a force, if you go by meat, can be in kilograms and stuff like this. But that right there, let's see, how many newtons are in a pound? I used to know this. Is it 5 point something newtons in a pound? Okay, if I check that on Google Earth. I'm just trying to remember, because I don't do this often, but it's important at least you have a feel for it. I think it's about 5. What'd you get?
You're saying 1 pound force is about 4.45 newtons.
Yeah, 5 newtons in a pound, roughly, 4.45. So divide that by 4.45, and you'll get what? The pounds. Can you see the 10 to the minus 9 pounds is about, why are we talking about that? That's the kind of force it is. Do y'all agree with this class? It's very small. Just perspective is important. What's the next part? Now change the sign.
Change the sign of Q2 to negative 4.
Now let's do this and talk it through. Over here, now he's saying this, make that minus 4 nanocoulombs. Now just think about it logically, right? Does this electric field from that one change?
No.
What happens to this electric field?
It just reverses its direction.
Now it goes like this, right? Now that, I'm sorry, not that way. It's going to reverse this way, correct? Oh, sorry. This way, like that, right? Now this is going to be E2. Do you agree with that, class? What do you see just looking at it? Can you all see it? What are we really going to get when we add those two? You see how the vertical components cancel? Everybody, can you see it open? You see that or not?
Mm-hmm.
Here's the vectors, look. This is E1, same exact magnitude as E2, here's E2. This angle right there is this angle. Can you see the vertical components will cancel, the horizontal or Y component will add, right? Y'all with me? And it'll be in that direction, which is positive A1. So to get that, what do? Well, look here. I'm going to get, to see what the force in the electric field.
Both.
All right, so I'm going to get the electric field first, then the force. The electric field from that, you can see what happens. Before we had 0.4 AX times this stuff. Now we're gonna have 0.3 AX, right? And really that means the electric field, this is part 2, at that point, which is, what is it, 004 or 400? The electric field is going to be, well, 9 times 4 is 36, right? Now I've got 5 cubed down here, that's 25. I'm going to keep that 5, one of those 5s, and now I take 5, 3 into 5 is 0.6, right?
Mm-hmm.
And I have to double that. Do you all agree with that?
Mm-hmm.
So what's that going to be? That's, that's going to be, 0.3 here. So that's 0.6, it's 1.2, and this would be in the AY direction. Can you tell me what that is? This is the field, of course.
1.728.
1.728 volts per meter AY. Finally, what's the force at that point? At 400. Just Q3 times that. What do you, times the electric field, what's that going to be?
1.728 nanos.
1.728 times 10 to the minus 9, and that would be newtons in the AY direction, correct?
Yep.
And is that answer in the book or not?
You didn't give us the answers, but that's what I got.
Because I'm sure, I'll post them, I guarantee that's right. Basically, if we did, unless I did something really stupid, I didn't say. That's the answer. You got that, class? Go ahead.
So why did you change to 0.4 to 0.3?
All right, when we take, first of all, this is 0.3 over 5, right?
Okay, yeah.
So that's 0.6 over 10.
Okay.
0.6 in other words, right? 0.6, you got to double it, it's 1.2. That's, and some of this stuff I may be doing a little fast and I don't mean, go ahead.
Why is it 0.4 over 5? Isn't it just 4 over 5?
It's, no, 0.3, right?
Why
It's
is
the
it-
AY direction, AX cancels. Vertical is AX.
Yeah, but why is it 0.3 as opposed to 3?
It was 3 over 5 cubed, right?
Mm-hmm. Yes.
So I made it 3 over 5 over 5 squared.
Yeah.
3.3 over 5 is 0.6, isn't it?
Yes.
3 over 5 is 6 over 10 or 0.6, right?
Okay.
0.6 times 2 is 1.2. That's the only reason I do this, but you can run it in the calculator. I'm not trying to do something here deceptive. You all with me? Okay. This is just showing you how to add these things. But you've had this in electrostatics, right?
Yep.
Remember when you had that these are the trivial problems. A couple of charges, you want to force on a third charge, add the 2 electric fields, and we could extend this to n charges. You can have charges everywhere. The real deal is you need the electric field for point of observation. Now, I didn't talk about spherical or cylindrical coordinates. I'm going to do that, but let me just preface this with, before I say anything more, how many have had cylindrical coordinates? Polar coordinates, whatever you want to call them. You guys have it? If you took mathematics here, you've had them supposedly. You didn't take math here?
Yeah.
Did you have them? Did you have them?
I don't remember.
Did you take all your courses there?
Yeah, I did.
You should have been exposed to it. I mean, polar is just one. We'll do polar first. And the only thing, or cylindrical, the only thing you're talking about now is finding, this is always useful when you have something that is cylindrically symmetric, means it looks the same way in every direction in terms of an axis of symmetry. And I'll give you examples of this. When I do these coordinate systems, then I'll get into some of the real applications of this stuff. This gets a little more complicated than physics. Actually, some of the stuff can be really complicated in the older books, but you want to see the principle at work, not try to just bend your mind with unnecessary detail. Okay, I had a really good prof for this, well, his name was Jerry Locks, I remember. He looked like he was in a chronic state of depression, but because we were so stupid. He was a good guy, really good professor. So, when we talk about cylindrical coordinates, we're really talking about this. just the z is the same in both. So if we have x, y, and z coordinates, and we want cylindrical coordinates, we don't even worry about z. Z is z. So z stays the same. But here's what changes. If that's x and this is y, and we want to talk about a point here that's x comma y. Y'all follow me? So take a radius vector from the z-axis, which is this origin, to there. You're going to get a distance. It's a radial distance to that point. It's called or labeled rho. That's the symbol. It's the Greek letter rho. What that is simply going to be equal to, let me put it up here actually. It's rho. And rho here is equal to simply the square root of x squared plus y squared. That's all it is. With me? You probably had this. Now, this angle that it makes with respect to the x-axis in a direction so that you're looking towards the y-axis, if you think about this, I'll try to do this one. If you think about x, y, and z, and you talk about a vector r here that's in spherical coordinates, if you take the projection of that vector into the xy plane, it becomes rho, and this would be what I'm calling phi. Now phi right here is really tan minus 1 of the opposite, which would be y, over the adjacent x. It's this angle. It's the angle it makes with respect to the x-axis. Do y'all follow me? You can forget about z. It has no bearing. Nothing changes. So that's phi. That goes here, and rho goes here. That is really the relationship between cylindrical and Cartesian coordinates. And why I'm at it, I'm going to talk about the differential lengths. So, you know how in physics and stuff you always have like F dot dl, right? The differential length is important. It's different in the different coordinate systems. If you don't know this, write this one down. And I'll try to keep them all up here and not erase them. So when you talk about dl, the differential length, if you're in Cartesian coordinates, it's simply dx ax plus dy ay plus dz az. You'll notice it's a vector. Now, if you're in cylindrical coordinates, this is obviously it's Cartesian, right? X, y, and z. Now, dl, if you're in cylindrical coordinates, that's going to be in here. I'm going to try to draw this. Maybe a little bigger. dz stays the same, but notice this is rho, and this is phi. So if it wobbles a little, if you get a d phi here, just try to understand, I'm showing you this being a small change in phi, this would be x, this would be y. And we take a look at this point right here, and we want to know the differential length associated with it, okay? I'll write it down there in a second, but just follow it. Now, you can go d rho. You all see how d rho just goes out that way? So it will be really d rho a rho. This next one's the important one. But what happens when this wobbles a little? How far does it move? Just think about it, from here to here. Think of a wiper on. Well, the tip of a wiper moves what? The radial distance, rho times d phi. Y'all follow me on that? So now, this becomes plus rho d phi a phi. It's no longer just d phi a phi. All right, you got to multiply by rho because rho's the wiper arm, and when this wiggles a little d phi, the tip there moves a lot. You with me? And then what's the last one? It'll just be plus dz az, right? So over here, I can say that this is simply d rho a rho plus rho d phi a phi plus, and then it's going to be dz az. Now, since I'm at it, I might as well talk about the differential volumes and differential surfaces. Now, if you're in x, y, and z coordinates, I'll put that here. By the way, let me tell you where this is in the book, because you have your books, I hope. Does anybody have a PDF of this book? You do? Could you do me a favor and send me that?
Yeah.
And could you edit that out of there? So I don't have public are calling, what are you doing here? It was a joke. Yeah, we find it funny. All right, so if you go to blah, 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 I'll tell you where I'm going. Ye. In your book, I'm going to reference this in a second. Go to page 132. In your book, there's a differential volume and cylindrical coordinates. I want to get there. And then, I don't know if he has spherical. Yeah, he kind of does. In spherical is 128. Then look on page 128 of your text. Can you hear me? Okay. 128. And I'll do the Cartesian ones. And I don't even know if he has Cartesian in there. But oh, yeah, it's on page 121. So, the next thing I'm going to talk about, I'll do spherical coordinates too, then I'll talk about these differential. I'll do the differential length in spherical coordinates, differential surfaces, but I want to do spherical. How many have had this cylindrical stuff now that I put it up there? Y'all with me? Have you had? And you? Do you remember it now?
It rings a little bit. I'm not sure which map it was.
In mathematics and physics, they show this. I
It
guarantee you.
was Cal 3.
Yeah, it was calculus 3.
I guess
Yeah.
it counts right here. So.
They should have done it in physics too, no?
No.
They didn't go this in depth in physics. That was pretty much
They just did Cartesian.
Okay, well, normally they do everything spherical. There are, I believe, 10 what are called separable coordinate systems. It means the axis is orthogonal. Here, cylindrical is orthogonal. A rho, a phi, and AZ are always orthogonal, 90 degrees to one another at any point. And you'll see that cylindrical they are as well. When I was graduate school, by the way, I'm not a fan of doing a lot of this proloid, spheroidal coordinates, or all these things. They're created so that the coordinate system is easily applied to things like proloid, spheroidal. If you think of something that looks like an egg, right? Right, you would like something so the surface of that egg would be part of a measurement for that system, all right? That's called a proloid spheroidal. With spherical, if things are spheres, it makes sense to have spherical coordinates because a spherical surface, R, is at a given radial distance, which you're going to see is a spherical coordinate. So coming back to this, when we're in spherical coordinates, now come down here, they're shown in the book. If you got a page number, you can tell me that's X, that's Y, that's Z. Usually, not always, but usually Z, if given a choice in 3D, is the vertical axis. Doesn't have to be. It doesn't really matter, but usually that's the way it is. So when we look at this, let me get a reference position in the book so I won't lose you. For spherical,
That's
I know
124.
he does it. Just don't know where. All right, he has it on page 127 on the top. He shows him about to show you. So I have to pick a point, an obvious point that I can discuss. I'm going to use a blue marker, and hopefully it'll work. Come over here and just pick a point. So I'm going to use it in X, Y, and Z. I'm saying this point has X coordinate, Y coordinate, and Z coordinate. And here's the origin, 0, 0, 0. It doesn't have to be this way. With me? Now, here's where you pay attention. The first thing you have to do is define a radius vector from the origin to the point where the position is in X, Y, and Z, okay? We'll label that capital R. In his book, he may have small r, but I'm going to use capital R. So what is R? Well, R is always that distance. All these are orthogonal, right? So it's going to be the square root of what? X squared plus Y squared plus Z squared. That's the radial vector. Can you all see that? Those yawns get me too. Now, if I take a projection, and this is something, assume you have a flashlight or the sun is shining down on this line, way up on the z-axis, you get a projection of this, and the shadow would be this. This is actually rho. That's rho vector that we were talking about a second ago in x, y. Z equals 0. You with me? So that projection rho is going to be, now the angles we use in spherical coordinates are the same as cylindrical in terms of azimuth, where you have an additional angle. This is called theta. You all with me? And it's the measurement from this, if you look at the z-axis, and you take a look at the angle the z-axis makes to the radius vector, that is theta. You all with me? Did you have this anybody before? And Cal 3?
Yep.
Okay, good. Did you have it, Chase?
Yes, sir.
You didn't do it? Did you?
I took Cal 3 and somewhere else.
Okay. All right, but you follow me on this? That's all it is. Yes?
So is the coordinate system for spherical r comma phi comma theta?
It's really going to be, the point would be the radius vector r. Now he'll have a small r, but it doesn't matter.
Yeah.
R, then it's going to be, from there, it's going to be theta and then phi. Let me show you his ordered points. If you look on 127 equation 320, he shows you a vector, and it's r theta phi is the order. But here's how you get it. I'll tell you how you always get this. Just hear me now. Well, the way you always get the coordinates is something where we do something cross something. If you have a right-hand rule, if you look at like x, y, do you remember cross products class?
Yeah.
All right. When you looked at the ordered pairing for Cartesian coordinates, you had x, y, and z, right? That would be an ordered pair for a point defined in Cartesian coordinates, right? Now, if you look at this and you talk about something, if you go ax and you're going to do cross into ay, what is that going to be? X crossed y is z, right? Do you remember this? You take your right hand, take your index finger, point in the direction of the first vector, ax. All right? Then use your thumb as a hinge point, rotate your index finger into the second vector, ay. Your thumb points in the resultant vector, all right, or az. Do you remember this at all? How many remember that? Okay, good. Now here's the way I always do it. This is az. Anytime you have a y crossed az, you're going to get ax, right? But here's the way I normally tell people to think about this. I do this. I just have x, y, and z. This is a crossing order. And then back here. What I've shown you are always going to be positive if you go around this way. If you go ax crossed ay, you get plus az. Ay crossed az, you get plus ax. Or az crossed ax, you get ay. Now, if you go the other way, it's negative. So az crossed ay is minus ax. Y'all follow me on this? And you can go through the permutations. Y'all, did you see something like this before? I don't know how they teach it over in physics or in math in Cal 3, but this is the way that I've done it since I was in school, where you're sitting where you are. Now, when you have cylindrical coordinates, might as well do this before spherical, and you'll see. When I have cylindrical coordinates, what actually happens, and I'm just trying to give you a video picture of this. Don't worry about this. Don't write it down. Just watch. If we have cylindrical coordinates, we've got a radius vector rho here. Oh, maybe that's not the best way to show it. Maybe trying to show this in the same plane. Well, call this radius vector rho. You have an A rho. I'm going to manipulate this. Like so. Forget about z, it doesn't matter. If this is x and y, we know we have rho, we have a rho, we have a phi, and we have az coming out of the board. Y'all with me? So a rho crossed a phi is a going into the board. Wait a second.
It'd be out of the board. Right here.
I got this. I have this drawn incorrect.
It'd be,
Actually, this
it'd be
is
out of the board, right?
this is phi,
This way, I don't remember.
and this is d. This is going to be
Or
a
actually,
phi, and yeah, it has to be that way. So it would be a rho crossed a phi coming out of the board would be a z, x, y, z.
yeah.
All right, I drew that wrong. I'm sorry. You with me, class?
There it is. This is rho, v, and then z.
You're like that.
And then for this one, it would be rho, phi, phi z, all positive this way, all negative. You get the hang of this once you do a few more. Now I need to do spherical, so I can explain this a little better, because I need the coordinate system before I can talk about differential length and differential surface. So, come over here, and now we're doing spherical coordinates. You can see one thing happening. This is R, right? That's radially outward. Now, the projection down here would be what? What would rho be? We have R here. What would the rho be on this one? The projection onto the XY? This is not a coordinate, spherical coordinates, but I want to show you this because we just talked about it. Wouldn't it just be this times the sine of this angle? Right? If we had this angle, it would be the cosine of that angle, right? But the cosine of this angle is the sine of that angle, right? So rho would be actually the sine of theta, right? And it's times R. You get it a couple different ways, but you all follow me on this? I mean, it's the projection of R on the XY plane. That's all that rho is, right? But this is the angle that we need. How do you get phi? Right? Well, what is phi going to be? Now, just draw rho and x. So if you have the x-axis here, here's my rho. I got that. And I want to know what this angle phi is. Think about this for a second. Well, what is it? Rho times the cosine of phi, this is one way to do it, would be x. Do you agree with that? That's one way. But I'm looking for this value right here. Another way would be what? The y value over x. So I could say that y over x, inverse tan minus 1 of this would be equal to phi, right? Opposite, this is y. We're in the xy plane. You all with me on this, class? But you can get it a lot of ways, as long as you can visualize what I'm talking about. That's phi. You can get it just from these coordinates, right? If I want phi, I just need y and x right there, don't I? I don't care about z, correct? But that's what it really is. It's a projection of this vector in the xy plane. So, phi you got, and theta right here is what? Theta, if you wanted to get it, technically it's what? It's going to be rho over r, right? Take a look at this. Rho over r going to be inverse sine of that. So it'd be sine minus 1 of this would be theta. And by the way, there are a lot of ways of getting these things. He shows the drawing that you should study and at least appreciate. On the top of page 127, he gives different formulas for theta. Y'all with me, class? And he even shows you the projection. If you just have r theta and phi, how you get x and y, and it's on equation 3.19. All this will be second nature to you after a while. It's real simple. Now, the differential, now that I got the coordinate systems up, let's do the differential length in spherical. So in spherical coordinates, let's do it here. I want to put it down here. That's cylindrical. So what's the differential length in spherical? Which is a good question. So we'll come back over here, and if you use that drawing, you might be able to see it better in his book. He has this on page 128. Look at the top there. So this point out of here, let's assume we're going to move it differentially. In this direction, it'll just be dr. So it would be dr AR. I don't even know if he shows this in the book. I think he does. See if you can find dr AR. He usually uses small letters. If you can find the differential length for spherical coordinates. I don't know if he's got it here. But I'm going to send you, can you do me another favor? Send me in that email.
I already said it.
All right, or send me another email that says post differential length, post differential length, volume, and surface on OneNote. I'll give it to you because
Okay,
it's,
post differential.
just put post DIF space COR, coordinates. I'll take care of it. That'll remind me.
I'm not going to formalize it. I'm just going to send that.
Huh?
Oh, I'm not going to formalize it. I'm just going to send that. and
Please, I
tag it.
get that. That's all I need. All right, now, that's the differential length. If you look at the bottom of page 128, maybe you can see this. If you look, can you all, do you have your books, guys? Do you have your book or not? Here, you can use mine. Look right here. Now, if you look at that, take a look, 128.
Oh, yeah.
All right, take a look at the length right there. When you go radially away, you see how it's just VRAR? All right, now when you go, and it's going to be a little tough to show. All right, now if you just hold that wiper on constant and you go d phi, right, where this becomes d theta, you'll notice that this distance is going to be r times d theta. Can you all see that? Because the wiper on it, right? I wiggle a little d theta. The length here in the theta direction is going to be r times d theta. Take a look in the book, in his figure there. So this is going to be plus r times d theta, a theta. With me? Please try to just focus on this part. Now, even though there's a lot of extra information here, now when you take the projection of this down here, that's really rho, right? Rho is equal to r times the sine of theta. That's what this is, right? Correct? All right, what happens when it wiggles with respect to phi? That tip moves, right? So it's going to be r sine theta d phi. And that means the a phi component, and I don't have it in this book, I think, plus r sine theta, and then it's d phi a phi. That's the differential length in spherical coordinates. And does he have that in the book? You've got mine, but take a look for a second. He has differential length, I think, in Cartesian. I don't know if he has it for spherical, but I'm going to give you them all. I'm going to give you differential surfaces and volumes, okay? Are you with me so far?
What does that last part say again? Is it r sine theta d phi a
Yeah,
phi?
yeah, it's got to be, look,
That's it.
you need this projection, right? We're gonna wiggle phi, right? And that means it's got a length rho, which is r sine theta, and you wiggle it, it's times d phi. That's the way I think of it. Agreed?
Yeah, I gotcha.
Now we got to get the differential surfaces and then volumes. He's got a great picture of the differential. Let me just do it this way because you can see this. If we are in Cartesian coordinates, guys, I'm going to build a little differential cube. That's how you do this differential surface. If this is the axes, if we have x, y, and z, this is our coordinate system, then you've got to build yourself a little cubic model here. This distance in this direction would be dx. This distance would be dy, and this distance would be dz. Can you all imagine that? Just x, y, and z. Now we put dx, dy, dz for the heights. Remember, they're differential, so they're approaching zero, but they still got a little bit of something. Now, if you look at a differential surface, it depends which one. That's a box. It's got 6 sides, right? Now, a differential surface has both a magnitude and a vector sense to it. So the top one, the differential surface for the top one, ds of the top right here, that would be equal to the differential in this way and this way. So it's dy dx. And it would be in the AZ direction. The third coordinate always is different or perpendicular to the other two. Now just take a look at this, see if it makes sense. A differential surface has a magnitude and a direction. Generally speaking, if we use the right-hand coordinate system, it always points out from the center of the differential volume, the differential surface. You with me? What's the surface right below it? If you can imagine, go straight down the bottom surface right here. What's that going to have a value of?
Minus.
Same d phi dx, but minus az, correct? So pointing outward. Can you all see that? All right, now what's the differential surface right here?
dx, dz.
It'll be AY.
in the AY
It
direction.
would be dx, dz, and the ay, right? All right, what about the surface right here, other side?
DZ, DY, AX.
dz, d what? I mean, dz, dx, right? But it would be minus minus ay, right?
Oh, you talking about the one on the back?
Yeah,
Yeah, I'm trying to.
Oh, sorry. I thought you were talking
My
about
drawings
the
are
one
horrible, but you
Right.
follow me on this?
Gotcha.
Can you all get this differential surface bit? Remember, it's pointing out from that little cube.
Yeah, that makes sense.
All right, so you got differential surface. I'll put, not sure I want to do this way, but I'm going to do it. So for Cartesian, it's just going to be sum dx, dy, and then, or maybe I could put dx, I'll just do it this way, times a normal. How's that? And you can rotate from dx, dy to dy, dz, to dz, dx, and it's got to have a perpendicular that's perpendicular to both coordinates. But you all follow me? Not done rigorously and mathematically, but I'm trying to give you an idea. Everybody with me on that? What about the differential volume? That's differential surface for Cartesian. What about volume? Just think about it. Volume is a scalar. How do you get the volume of a box? Height times width times length, right? That's a nice one. dx, dy, dz. Can't go wrong there. It's easy. Now, next, we're going to do cylindrical. That's a logical way to do it. It's easier. Yes, sir?
Would the volume not be x dx dy in the az direction?
Now, this is the volume of this box. You'll notice it's dyy, dx this way, dz height. There's no value of x, y, or z per se. It's a differential. You agree with that? I know it's at a point x, y, z, but the differential has nothing to do with the point of observation. All right, next, come over here and we're going to do cylindrical. I'm going to do it here. Most of this stuff you're going to think is too obvious for me to spend time on, but I've learned over the years there's usually small gaps in your understanding. Small but important gaps. Not always, but sometimes. All right, now for for cylindrical, what changes? In cylindrical coordinates, we have rho, we have phi, right? And we have z, correct? So I'm going to have to build this. Usually they put it out here, but I'll try to put it here. If you think about this, I showed you a curved surface. So. This ain't gonna work. All right, this distance is going to be just d rho. This distance, the wiper arm's movement in the xy plane would be rho d phi, and the vertical component is going to be dz. Can you all kind of imagine that? Just assume you have the Cartesian one, but now the edge out here is rho d phi. That's still d rho, that's still dz. So the volume, the differential volume would be what? We got differential length. Might as well do differential volume. Well, how about we talk about ds first? We'll do ds. There's 6 of them, right? If it's a cube, it's a bad cube. You all follow me? So what is ds of, say, this outer surface? Can you all follow me? What would that be? Anybody? Outer surface. Well, it's pointing in the a rho direction, right? So this surface right here would be a rho. It's the direction. And what's the height?
DZ.
dz. And what's this?
Rho D.
Right.
Phi.
Rho d phi. Now that would be the outer one, right? What about right back here?
Equal and opposite.
Same, only minus a z, or a rho, right? You agree with that? What about the top? D rho?
Rho D Phi.
It would be rho d phi this way times d rho az, right? Below, directly below, minus az, right? How about this surface? Be careful now, I want to tell you this. A phi points in this direction. A phi is going this way. All right, so vector sense would be minus a phi, right here. This is this surface. And it'd be times the height, dz, times this, d rho. Can you all follow me on that? And that's basically how you get the differential surface. It's really the differential area times a vector that shows the perpendicular moving away from the center little cube. All with me? Okay. So what's the differential volume in cylindrical coordinates? dV for cylindrical class. This is
Rho, d rho, dp, d.
it's going to be first d rho, right? Times rho d phi times, the order is unimportant, times dz, right? Isn't that it? It's the differential sides. Good. I hope I'm not boring you about this. I'm trying to make sure you see this, because I trust me on this one. I have done this, and there's always these minute gaps, usually in cylindrical or spherical too, where I was saying, huh? But you have to see this. And remember, the theta is measured from the z-axis to r. That's the big deal. Because some of the guys that come from aerospace, they always use they use elevation azimuth, and elevation is measured from the xy plane to that radius vector. It's the 90 minus my theta. So make sure you get that. Okay. Next, got differential volume, surface, and length. Now we're going to do some of the problems. We're going to do some problems that are classical problems that you've done.
You didn't define dV for spherical.
Didn't I just do that?
That is
Oh,
cylindrical.
Oh, so what's it for spherical? I'm sorry. dV would be what? R, right?
Yeah.
Let's do it this way. First it's dr. I'm so sorry I did. It's d. I'll use small r. It's that, right? Now you got to take, first it's rho times d phi is in the horizontal plane, the tip in the horizontal plane. So rho is equal to what? That's equal to r sine theta, right? And it's going to be d phi, correct? Right?
Yes.
So it's r sine theta then d phi times what? R, right? R d theta, right? Follow me? And that would be the differential volume. So the nice thing about that is that's going to be r squared sine theta, and that's going to be dr d theta, or d theta d phi, and the order doesn't matter there. But that's the differential volume. I'm so sorry I didn't put that down. With me? That's in the book. I know. All right. Now, without further ado, I'm going to go and calculate the differential electric field from a chunk of charge, and then integrate that differential electric field, or integrate the actual spans, or where it exists, for classic problems. I'm going to start with something most of you guys know. It's going to be a ring of charge with a certain charge density, okay? Then we'll go to the line charge, and we'll do them all. Okay. I have got all sorts of problems. Gosh, I've got electrostatic problems like coming out of my ears sometimes. I've got so many different books and cataloging all this stuff. Classical problems, they're from old books from the 1920s to the 1950s. Okay, these are called canonical. They're really classical problems that everybody talks about. So if we have this is going to be called a ring of charge. It's in this book. It's a ring of charge. So this is going to be my x, this is my y, and this is my z. And now I'm going to put a ring of radius a down here. Just follow this. It's going to have a radius a. And I'm trying to draw it. You draw it better than me, probably. This has a radius A, and there's a charge density. Now we're talking about charge density. Before we just took a look at charge, coulombs. This is going to be so many coulombs per meter. It's called the line charge density on there. And this is the line charge density. The units of this, of course, are going to be coulombs per meter. That's where it's on here. Do y'all follow me on this? Think about taking a charge Q and then dividing it by 2 pi a, the length of that. That would be the charge density, the line charge density. Should make perfect sense. Everybody? And what we want is the electric field on the z-axis. So I want the electric field on the z-axis at any height z. Can y'all follow me on this, guys? This is a classic problem. So what you do is start with the electric field from a little chunk of charge. So I come down here. That's my distance r. Really, it doesn't matter if it's capital or not. Then r is going to be equal to, in magnitude, well, I'll do it this way. This value r, measured from here to the point of observation here, this is where we want the electric field, is going to be equal to, really, if you think about it, it's in cylindrical coordinates. You can forget about phi, the phi difference, and here's why. I want you to listen to me on this. Most of you can see if we get, for the radial distance difference, so we want the actual coefficient of AR, it's the position of observation is 0r. You agree with me if I'm on the z-axis? And here it would be A, right? So this position of observation would be 0 minus A, or minus A rho. You can put R there, rho there if you want. The next thing I'm going to put is the phi coordinate, but here's where it loses its meaning. You see how if you're on the z-axis, there is no phi definable, right? You have to be off-axis, 7 point x, y, and z to have phi defined, so we don't even worry about phi. But for z, what is it? Well, it's going to be point of observation, which I made to be z. Say I want the E field at, and this is going to be in cylindrical coordinates at 0, 0, it doesn't matter than that one, and then I'm going to have it z high. So this is going to be plus z a z. I hope you can follow me. Does this make sense to everybody? That's just a vector from here to here. That's vector r, by the way. So when I want my electric field here, what I'm going to do is get the differential electric field from a little chunk of charge, dq here. We're assuming there's a little chunk of charge here, and I want the differential field here. This is important to see. So when I look at this, that differential electric field would be equal to k, that's just 1 over 4 pi epsilon naught, times dq over r squared in the AR direction. Now, do you all follow me? I'm just putting down the general formula as if we were in Cartesian, or as if we had just one chunk of charge, only I put down dq, not q. Now, what is dq? Well, if you think about it, what would dq be? It would be dl, right, times the charge density. Do you agree with that? So this dq right here would be dl times the charge density rho L. Now, for this one, what is dl? Now, you're going to have to just take a look at this. Everything's held constant except what? The phi variation, right? If we're right on the z-axis, we're at a fixed distance a, so it's really ad phi, or the radius a d phi, and it's times rho L, and that would be the differential charge. I'll put that down here. So this is going to be K times, and here it's going to be A d phi times rho L. It's over r squared. Can you all see that the magnitude of r vector is just going to be square root of a squared plus z squared? Can you all follow me on that? So this becomes square root of r squared plus z squared, but that is taken, I got to square that, so I might as well leave it as r squared.
Wait, I have a question. Is the distance from the ring to the point?
Not ring. Oh.
Is
I'm
r
sorry.
squared.
Here's what I should say. This distance right here, right? That distance, that's a triangle. If you look at this, trying to draw this in a way it's meaningful. That's Z. This is A. This is the distance R would be square root of Z squared plus A squared, right? Y'all follow me? I'm sorry if I didn't draw it well.
Yeah. So that should be a squared plus z squared.
Yes, yes, yes.
I'm just making sure.
You are right, and I am wrong. What did I call it? I didn't call it. All right. I mean, I didn't call it A here. Now this is squared. You agree with that, class? Now I have to multiply it by a unit vector. Here's where you pay attention. Unit vector is always vector R over magnitude R, right? So vector R I have as equal to, right here is going to be minus A rho plus ZAZ all over the magnitude of that, which is square root of that and that. Now, if you look at this for a second, this right here is really A squared plus Z squared. And I'm going to multiply that by the square root of A squared plus Z squared, so it actually comes out to be this. It's just going to be A squared plus Z squared to the 3/2 power. And I hope you see that. Can you all see that? Now here's something that it's a little different in Whitmore's book, but you have to see what I'm about to show you. Now if you look at this, I mean, this is how Whitmore's book does it. If you look at this carefully, you're going to see that this thing, as we integrate around here, it spins like this, right? All the horizontal components will cancel by symmetry. That's how he says it. So he'll ignore the rho component and just integrate the z component. But here's another way to do it. If you take this as the differential electric field, you don't have to write this down, but please, this part, watch, because I'm going to slow down and make sure you see this. If I take this as the differential electric field, before I integrate it, I'm going to say the differential electric field will be equal to what I have there, so it's going to be K times rho L times A, and then all those are constants, by the way, and now I'm going to put my integration, I'm going to just put a differential here, I'll do the integration in a second. So here I have minus A times A rho. Well, A rho in Cartesian coordinates, if you want to put it into Cartesian coordinates, would be cosine of phi AX plus sine of phi AY. Now, I'll show you why I'm putting that down there. If you think about Cartesian coordinates and just follow them, this is X and Y right here. If we take a look and we have the unit vector A rho. A rho is at some angle phi, right? What's the magnitude of A rho? 1. Y'all with me on this? So if I want this unit vector A rho, and I want to take it in terms of X components, the AX component would be simply the sine of this, or cosine of this angle, sorry, cosine of that angle, times AX plus the sine of that angle times AY, and that would be A rho. Both have a magnitude of 1, and again, it's just taking this and putting it into an X and a Z component. You all follow me? Now, if you have that, so I'm going to put it here, this becomes simply cosine of phi AX plus the sine of phi AY here. It's all times A, plus ZAZ right here, and that's the d phi I didn't bring through here, so it's times d phi. That's the differential electric field. Can y'all follow me what I'm doing? Now, and I'm trying to, and this has to have a bottom part that is a constant, which is A squared plus Z squared to the 3/2 power. I just want you to listen for a second. I'm almost done. That's the differential electric field. If we wanted the total electric field on the z-axis, we'd integrate that differential electric field over the total length of that loop. Do y'all follow me? Now, here's what cancels, just by looking. I told you could get this from an argument of symmetry. But if you take this right here and integrate from 0 to 2 pi, because that would be all the way around the circle, right? 360 degrees. Then you'll see one thing. What happens when you integrate a sine or a cosine from 0 to 2 pi, or over a period? Or
It sums to 0.
it's 0. This goes away. This goes away. Only this is maintained. And you'll notice that when you integrate this d phi, this is z. It's not a function of phi. You just get phi evaluated from 0 to 2 pi times that. Or that means when I integrate this to get the total electric field on the z-axis, here's what I get. And this is in your book. I find that the E field on the z-axis, and that's really at 0, 0, z, if you want it this way, from a ring is simply going to be equal to k times, and that's 1 over 4 pi epsilon naught times rho L times A, which is the radius of that loop, and then it's going to be times the height, which is z, right here, and then it's times 2 pi, and it's divided by a squared plus z squared to the 3/2 power. I'm going to simplify this over here, because I'm out of time, Mr. Beck. I want to make sure you see this. So coming over here, if I look at this, that means for a loop at z equals 0, centered in the xy plane, the E field itself, and this is the one in the book, is going to be proportional to rho L, A, and Z, so it's times rho L times the radius times the height Z. All right, it's divided by 4 pi epsilon naught. Now I'm replacing k by 4 pi epsilon naught. Then it has a squared plus z squared to the 3/2 power. It's in the AZ direction, but there's a 2 pi here that comes out. This would be volts per meter. Can you all see how the 2 pi and 4 pi cancel? And a couple of important observations. This becomes simply 2. This is the one. You write it down. Put some exclamation points. Need to know. Now, when you look at that, couple of comments. Just look at the formula. That's assuming that the actual loop is centered. It's in the xy plane at z equals 0. What's the value of the electric field at z equals 0?
0.
0. What's the electric field at z equals 1? Well, I don't know, but it's positive, right? What's the electric field at z equals minus 1? It's negative that. See, because of the z? And that's true always, because if you have a loop of charge, if you're above the loop, the electric field's going to have a positive z sense. If you're below the loop, it's in the minus z. I'm going to give you a few more problems. Now, I got a question for you. Would you mind having a quiz on Monday? We don't have a Monday off, right?
We don't have Monday off. Okay.
Instead of Friday, because I didn't get to cover the material I wanted to. I had to go through the coordinate systems. Please do these problems on Friday. We're really going to hammer it. And then on Monday, I get a quiz. Is that fair?
Yeah.
Sure, push it off again.